If some of you know, or some of you it's the first time, normally what we do is a short talk, and we call a mini, and then we do a full-length talk. And I introduce both of the speakers by telling you their bio and also making something fake about them. So you have to figure out which one is which. So we're going to introduce Tyler. Tyler McMullen is CTO at Fastly, where he's responsible for the system architecture and leads the company technology vision. As part of the founding team, Tyler built the first versions of Fastly's instant purging system, API, and real-time analytics. Before Fastly, Tyler worked on text analytics and recommendations at Scribd. Is that good? Is that how you pronounce it? Yeah, a self-described technology curmudgeon, he has experience in everything from web design to kernel development and loads all of it, especially distributed systems. If he wasn't in tech, Tyler would be crushing it in national hairstyling competitions. So let's give it up for Tyler.
Hi. Ooh, okay. I see. Oh, I have to use this deal. Okay, great. So, the paper that I was going to talk about is called Similarity Estimation Techniques from Rounding Algorithms. And I'm not going to talk about rounding algorithms at all. And I'm probably not even going to get into like almost any of the math in the paper because this is a mini, and also because I'm not an expert in that. Instead, what I'm going to talk about is how I actually use this in production to like build like a real large-scale system using the techniques that were described in this paper. Okay, right. So, so what this paper is actually about is locality-sensitive hashing. Who here knows about locality-sensitive hashing? Sweet, some of you, but not everyone, so that's awesome. Okay. So the particular LSH function that they talk about in this paper is like particularly easy to understand as far as LSHs go, and it's also super highly effective for like particular use cases. So I thought it was a pretty good one to share with people. Right, so we're going to talk about locality-sensitive hashing, but I wanted to give some of the reasons why we were like using this. So like, okay, so before we can talk about locality-sensitive hashing, first we have to talk about the curse of dimensionality. But I guess before we can get into that, we have to talk about cosine similarity. And before we can get to cosine similarity, we have to talk about vector spaces. And before we talk about vector spaces, we need to talk about feature selection. And before we talk about feature selection, we need to talk about nearest neighbor. Okay, so let's do this. I think we can do this in like 10 minutes. It's going to be fine. Okay, so nearest neighbor, you have some things. You have things, and some of them are similar to other things. Okay? Okay, so let's say we're going for A. Okay, we're going to find the things that are most similar to A, right? And so like, the idea here is that we're projecting this into some sort of space. It might be Euclidean space, it might be vector spaces, but it's some way, there's something that we can use to compare an object to another object in order to determine whether or not they are close to each other. So in this case, obviously, B is the closest. That would be the nearest neighbor. Cool. So what does it actually mean to compare things, right? We have to have some way to compare it. That's where feature selection comes in. And like, this is like a huge subject, but essentially like, what are our objects and what do we care about the objects? And so like, there are like machine learning systems that exist solely to find feature selection for like individual types of things. But, so let's use an example, and this is like relevant because the system that I built back at a previous company that used this was using text. Okay, so like let's say this is like our example document, right? So I was reading Vonnegut on like the plane ride back from Austin today, so I decided to put this one in there. Great, I enjoyed that. I don't know. Just go with it. It's fine. So the problem is that it's not terribly useful to look at the document this way. It's just a string, and as far as structure goes, that's not much to work with, right? So feature selection is the process of determining how we pull this blob apart into something with structure, right? So, you know, one example, we could just like treat it as a bag of words. And this is a pretty common way to like deal with text, right? And so in this case, it's just word counts, right? Like those are all the like counts of the individual words and that type of thing. And so like this is useful for just like determining the subject matter effectively. But there are other ways we could chop this up, right? We could cut it up into letters, right? Individual characters, right? So it turns out that this is actually a really useful thing to do. You can use this for, say, language detection, right? Or we could cut it up into, we could eliminate all the common words. And this can help to improve the accuracy when you're like trying to compare actual subject matters of two different documents. Or we could only keep the common words. And it turns out that this is really useful if you're trying to do authorship analysis, right? It turns out that even when you're trying to change your writing style, if you're like, if you're trying to like avoid authorship analysis, it's really hard for you to like get rid of the way that you use common words. Just as like an interesting aside, the relative rates at which you use the common words are like incredibly hard to change in your like personal writing style. You can like develop a signature of individual people based on that. Anyway, so basically the point is that we end up with features as a weighted set. Right, so we have a set of items, each of which has an individual weight based on like how often it occurs or how important it is in this particular object. So that brings us to vector spaces, right? So vector spaces are interesting because we can take our weighted sets and represent them as vectors. The problem with this particular thing is that every possible member of the set becomes a dimension in that vector space. So if we're talking about like, say, these words. This weighted set has 29 items in it, right? 29 words. However, if I'm representing this in a vector space, I need to have a dimension for every possible word. Of course, I get to decide what words I'll allow. So effectively, the dimensionality of the vector space is determined by the size of the vocabulary that you're going to allow into the system. In practice, when I worked on this in the past, the vocabulary that we used had several million words in it, right? In various languages. So thus, this weighted set would actually become a vector with millions of dimensions. It would just become a very sparse vector with millions of dimensions. The vast majority of them would be 0. So, okay, so that's vector spaces. Great. Okay, cosine similarity. So the reason we'd want to represent our weighted sets of features as vectors is because once we have them that way, there are really cool ways that we can compare them to each other. So one of those ways is called cosine similarity, and it measures the angle, or the cosine of the angle, between two vectors in an n-dimensional space. In short, the smaller the angle between the two vectors, the more similar they are. It's as simple as that. So if you're not familiar with like working in high-dimensional spaces or with high-dimensional data, the idea of measuring an angle inside a like million-dimensional space might not make a lot of sense, but an easy way to think about it is like this. So if you have like a 2D plane, right, you can measure the angle between like two vectors, right? If you have a 3D thing, maybe it's going like, maybe the vectors are like that. There's still an angle between them. As the number of dimensions increases, that is still the case, right? So basically, it looks like that. The dot product of the two vectors over the magnitude of each of them times the other. And remember, we're talking about vectors that have millions and millions of dimensions. So you might be thinking this seems like a really, really expensive way to measure similarity between two different objects, right? Cool. This is called the curse of dimensionality. Welcome. You're all in the curse of dimensionality now. This is like this for years at my previous company. This shit was like the bane of my existence. Also, it is kind of sci-fi as fuck. Yeah. Oh, really? Undefined? That's cool. Thanks, John. So basically, as the number of dimension grows, the space increases exponentially. And essentially, everything becomes further and further away from each other. The available data becomes more and more sparse. And so finding the nearest neighbor gets harder and harder. And in the case of like cosine similarity, it involves doing a vast number of operations, right? So you're essentially trying to like find the dot product between vectors that have millions and millions of dimensions. This is incredibly expensive, especially if you have like millions and millions of objects that you're trying to compare to each other. Okay, cool, great. Now, locality-sensitive hashing, great. So the idea behind locality-sensitive hashing is that we want to develop small signatures for large objects. And ideally, they can be compared to each other. And it's kind of like the core point. Like we could hash things and determine whether or not they're the same as each other. But locality-sensitive hashing, the point is that like we develop these hashes, these digests of the objects that can be compared to each other in some useful way. In our case, what we're trying to do is develop signatures that can be compared to estimate cosine similarity, right? So it might look something like this. We have our vector space here, let's say, and what we do in order to do like this particular algorithm in this paper is we generate a series of hyperplanes that like slice up the individual slice up the space, right? So we do this. We continue to generate them. Yes, cool animations, rad. And then what we do is we have our target vector. Right, so this is the vector that is like representing some document, some object, some picture, some whatever in the space, right? And so essentially what we do is we compare this vector to each of the hyperplanes, and we determine, this is the way that I think about it. This might not be the best metaphor to use for it, but it helped me to understand this thing because it was difficult for me. We essentially determine which side of each of the hyperplanes this vector is on. Is it on the left side or the right side, effectively? And so for each of those, if it's on the right side, let's say, metaphorically, we record a 0. If it's on the left side, we record a 1. And as you go through each of the individual hyperplanes, you can then build up a hash for each of them. And so by slicing up the vector space in this way, it lets us have a much smaller way of essentially triangulating where in the space this individual vector lies without actually having to record all of those millions and millions of dimensions. So the formula for it is really stupid simple. It just looks like that, right? So for each of our random hyperplanes that we've generated, we just take the dot product, and if it's greater than or equal to 0, we record a 1. If it's less than 0, we record a 0. As simple as that. And then the way that you determine whether or not two vectors are actually similar to each other or different from each other is just by taking the Hamming distance. And the lower the Hamming distance is between them, the closer they are, the closer the angle is. And so this can be used to estimate cosine similarity. So in real life, I used this technique at a company that had many, many millions of documents, like tens. I think got up to 150 million documents that we were trying to compare to each other. And in that case, what we did is we generated 256 hyperplanes, so which made it possible to have a then 256-bit hash that we were then using, right? So we generated a hash for each of the documents that was uploaded, and it then became incredibly fast to find other documents that were similar, rather than doing this incredibly expensive cosine similarity calculation. So in this case, we actually just compared each of those incoming hashes, each of those incoming things, to every other thing, because that was fast enough. Because it turns out that taking the Hamming distance of 256-bit numbers is incredibly fast on modern computers. So that's all I got. That's it. I'm done. Any questions?
We have questions. Wait. I have a broke. Okay. Questions?
If you ask me math questions, I'm just going to walk off the stage, just to be clear.
You couldn't have stayed anywhere further.
So how do you determine maybe the number of hyperplanes and also just what, I guess, where do the number of hyperplanes that you end up generating come from, and how do you determine that?
Yeah, that's fair enough. So the papers, some of the individual locality-sensitive hashing papers, the early ones, talked about this a bit, and I'm trying to rack my brain. It's been a bunch of years since I read those. So we essentially just tested out a bunch of them. We tried 64-bit hashes and found that there were it wasn't quite accurate enough for us. We tried 128, still not great. 256 bits, at least in our particular use case, we had very, very few wrong answers. It was incredibly rare for us to get bad answers to finding documents that were related to each other. So honestly, it was just trial and error.
Is this technique the same technique that's used for stuff like Shazam or Google-related image search, or do they use something else?
So I don't know what Google image search uses, although I would be really curious to find out. But it is, in fact, similar to some of the things that Shazam does, as far as I understand. I don't think they're doing exactly this particular type of locality-sensitive hash, but if I remember back to the individual paper that Shazam was using, it was fairly similar. Yeah.
Thanks.
When you set this up, you had, was this a word, there's actually a text example, right, where you were picking some number of words, and you got new documents in that maybe had a word you hadn't seen before?
Sure.
Would you, like how would you choose the component of the vectors you're using to do this in that new variable in a way that doesn't kind of...
Yeah, that's kind of an ugly part of this, and I don't know a great way around this. But in our case, when we developed the system, we already had so many documents that what we did was just develop a vocabulary based on the existing ones, right? So like in the case that you're going to be needing to add new like items to the vocabulary, essentially new dimensions to the vector space, I don't know how to handle that, and that would be really ugly and unfortunate.
And were you just doing the straight up like counts of words, or were you using a different feature set?
Yeah, so we were using bigrams at that point. So essentially each pair of words.
And that's why you had millions.
Yeah, many, many millions, yeah.
Okay, thank you.
Oh, thanks. Just kind of a question observation. Most hash functions try to mix and make things close together be very different.
Yeah.
Why didn't they call this locally sensitive compression? Hashing makes you think it's going to mix.
I mean, I guess that's an entirely reasonable question. I have no idea why they called it that, but like, I don't know. It like when I thought about it when like I was like first reading about this thing, it somehow made sense to me because I'm essentially just like, because it's not really compression, right? Like you can't really recreate a thing from this. It's essentially just, it could be like locality sensitive signatures or something, right? Yeah.
I don't know. I was just going to, what you said that it's not, you can't get it back.
Yeah, yeah.
More questions? Okay, Bob. I am going to be in the middle.
So if I just wanted to say there's a really nice library, if you don't want to implement this yourself, but you want to use it, called Annoy, which is short for Approximate Nearest Neighbors, Oh Yeah.
Wow.
And it's really nice. It does this algorithm, and it also has like an on-disk representation that you can generate in batch and ship onto servers and stuff.
Oh,
So.
that's fantastic. When we were reading about this and implementing it, it was like 7-8 years ago at that point, and so like I actually had to implement this shit in like fucking Java. Like fuck my life. I don't know.
Yeah, it's just a comment about the question about hashing. So
Please.
I think it was more the analogy not to hashing but to hash tables. In the original papers, they would use the signatures as keys in a table, basically just an array, and that's why it's called hashing. So I think it's a terrible analogy, but that was the original meaning,
Yeah.
I think.
Yeah, that's entirely fair. That's something like this particular paper didn't cover that at all, but some of the papers that came before this talked about an actual data structure that you could put these in that would make it faster to find things that were similar to each other. In our particular case, I found that like even comparing like tens of millions of these hashes to each other, it just wasn't actually worth it because I could do that in like a second. So yeah. Cool. Thank you.
Any more questions? Okay, thank you, Tyler. I think there's pizza, so we're gonna bring it in as well. Woo! Gilbert Bernstein is a PhD student in the Department of Computer Science at Stanford University. His work focuses on a range of topics across computer graphics, HCI, programming languages, including domain-specific languages, visual tools for artists and designers, geometry, and topology. He's gotten some awards in the past that you don't really care about, including Best Jean Shorts Wearing Award in the summer of 2012. And the only song that Gilbert can sing the only like rap song that Gilbert can sing at karaoke is, apparently I always pronounce this incorrectly. How is it? Amish or Amish? Amish Paradise. So yes. So let's give it up for Gilbert.
Thanks, everyone. So I'm going to talk. Do I need to stand in front of this? Is there another? I'll just grab this. What? Oh, that'd be awesome. But okay. Hi, everyone. I'm going to talk about a paper from 1988 called Spacetime Constraints. I was not an author on this paper. The authors were Andy Witkin and Michael Kass, which we'll see later. But I am giving the presentation. And part of the reason I want to talk about this paper is that I think there's a lot of interesting angles or dimensions to how one can appreciate it. So that's roughly how this talk's organized. I'm going to talk about how the paper was positioned, which I think is really one of the best positioned papers I've ever read. Okay, so to start, positioning a paper is really all about context, which means I need to talk about the history of computer graphics. In 1983, up at Lucasfilm, which was in Marin County here in the Bay Area, there was a group called the Graphics Group there. They had done the graphics, I don't know if they did it for Tron, they definitely did it for Star Trek II, The Wrath of Khan, the terraforming scene. So it's some of the very early computer graphics in the film industry. And they produced in the computer graphics group for SIGGRAPH this image that they called the Road to Point Reyes. Point Reyes, as many of you know, is up north of the city there. And they also named the rendering method that they used in this group the Reyes renderer, which was an awful pun. And what's interesting about this in '83, so the ray tracing paper, it's slipping on me the author of that right now, with the famous refracted sphere image was 3 years prior in 1980 approximately. And there's already a marked amount more realism, right? You have this reflection, you start having foliage. They're really trying to move towards a much more realistic image here. So this was a big deal at the time. The next year at Lucasfilm, a fellow by the name of John Lasseter helped produce the animation for something called The Adventures of Andre and Wally B. And the narrative is very, very sparse, but it makes a very nice technical demo of the foliage capabilities. You have this very luscious forest in the short. Then after this, the graphics group at Lucasfilm got spun off and sort of had this process of separating, and they became known as Pixar. And in 1986, Pixar, whose primary business at the time was producing a special computer workstation called the Pixar Imaging Computer, made this short called Luxo Jr. And so I want to show you a little bit of this short here. See if this works well. Great. So pay attention to the animation you have going on here, the motion of the characters, how there's all these little details, the wiggle, bounciness that produces a certain lifelike quality to the whole thing. So when this showed at SIGGRAPH 1986, there was really nothing like this in terms of conveying that sense of animation, not in the technical sense, but these characters are animated. They have personality. They appear lifelike. And what happened was then that year at the Academy Awards, this won the animated short. So it's the first computer graphics animation to win at the Academy Awards. And so this is a huge deal. It's sort of a small watershed moment for the community in '86. And I was giving this talk earlier today down at my research group. I'm a PhD at Stanford. And so my advisor, who was at Pixar at the time, had contributed this anecdote that I want to share with you, which, as I alluded to before, Pixar's main business was producing the Pixar Imaging Computer, not animation. They were very far away at this point, about still a decade away from getting Toy Story out, and they didn't think it was going to be technically feasible writing Moore's Law for quite a while, right? So they had to have some sort of plan in the interim. And so all of these movies were produced as tech demos. And this particular one, they sold this to the management because they were working on shadowing algorithms. And so they had motion blur and shadow algorithms in their renderer. And they were concerned about the fact that their shadow maps that they were building were not being motion blurred, and that this might be a big problem. So they really needed to do a test to show that this wasn't an issue. And that's how Luxo Jr. got made. So the next year at SIGGRAPH 1987, John Lasseter presents this paper titled Principles of Traditional Animation Applied to 3D Computer Animation. This is a very strange paper in the SIGGRAPH proceedings historically. There really hasn't been anyone like it, and I'm told it was somewhat controversial at the time because it was presented in the technical papers track, but there's not really, math and computer science in it. It's all about artistic principles of animation. Part of the reason this got in was because everybody really wanted to know how the heck John Lasseter pulled off Luxo Jr. So in this paper, I just pulled out a bit of the introduction here. I want to focus on a couple bits. Lasseter says that these keyframe animation systems that have come about, have only just recently come about, and they're going to enable people to produce more high-quality computer animation. Everybody agrees that they've certainly produced at least one high-quality computer animation at this point. However, he warns that they will also enable people to make a bunch of really shitty animation. And the distinction he makes is that this is because a lot of people are unfamiliar with basic principles of animation, which worked for hand-drawn animation, and that they're equally applicable to computer animation. He outlines 11 of these animation principles, and they're taken from various documents and wisdom, primarily developed by Disney, as they developed all of their hand-drawn animation over the early 20th, or mid-20th century. And so he also illustrates these principles with examples drawn from his shorts that he's done. So he has the Adventures of Andre and Wally B, a bouncing ball, and a Luxo Jr. lamp. So for instance, here, the principles of squash and stretch, anticipation, follow through are shown. Wally B pulls back before he dashes forward. And this helps convey that the bee is about to move in a direction. All of this, generates appropriate anticipation in the audience. So now we're at SIGGRAPH 1988, and the Spacetime Constraints paper comes out with Witkin and Kass. As I told you, positioning a paper is all about the context. So now I just gave you all the context. They recap this all super quick in a paragraph at the beginning of the paper, because of course everybody in the audience already knows all of this. It's a really big deal. And then they say this. They say, many of these principles of animation are concerned with making characters' motions look real at a basic mechanical level that ought to admit formal physical treatment. So what do they mean by this? Well, look at Luxo Jr. leaping. They say, well, if you think about this as a physical or pseudo-physical system, so in part Luxo Jr. with some sort of pseudo-physical muscles, in order to be able to make this jump physically, Luxo Jr. has to bunch up and then propel, and then when landing, of course, have to absorb the momentum of that jump. And that this naturally leads to things like anticipation, speed up and slow down, follow through, right? So they're making this rather bold claim about where some of these principles of animation might come from. And they make this explicit. They say these arguments that they put forward like that make nice post hoc explanations. And then they say, we're going to take this a step forward, and we're going to use this idea to try and generate the motions themselves. And they pose this somewhat as a scientific question, right? If we can do this, then how much of these principles is really sort of subjective artistry versus just a natural consequence of physics? So sort of condense that down, these are sort of the questions they're posing to the community. And as many of you may know, being in technical communities yourself, for the SIGGRAPH community, the answer to these questions was yes. It didn't really matter so much about this as a scientific investigation. This was pushing all the right buttons. If you're a technical person working on this stuff, and you just heard this talk last year saying, oh, well, it's all about, these artistic principles, and someone says, but I bet we can automate all of those artistic principles if we just know a bunch about this technical subject, which is physics, right? You don't even have to work to push this whole line on everyone. Everyone buys into it immediately. It immediately sets this agenda in computer animation and computer graphics that we can make tremendous progress by understanding the principles of physics and applying them in these animations. So that's why I think the positioning of this paper is amazing. The second thing that this paper does is, even though people might buy into that sort of argument, at that point in the 80s, a lot of the computer graphics community weren't trained as physicists, and they didn't really know necessarily how to do sophisticated computer simulations of physical phenomena. And so they introduced some of those key concepts that a lot of people might not be familiar with. And variational mechanics is sort of a key one here. For this, they use this example of having a particle with a jet engine strapped to it. Let's just go ahead and consider this physical system and walk through some of that math. So there's some gravitational force acting on this particle. So here's, like the gravitational acceleration constant, 9.8, blah, 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 blah. And then there's some sort of control force, which results from the jetpack spewing fuel out, right? And so these two forces act on this system, and this results in some motion over time. And we can think about that motion in terms of the force as a function of time and the position as a function of time. And write down some simple equations of motion, right? So, okay, our equation of motion here is just saying, yeah, the gravitational acceleration times mass plus this control force is equal to mass times the acceleration, instantaneous acceleration of the particle. So you should notice that this is really just F equals ma, right? So Newton's second law, hopefully not too strange to anyone. Okay, so once we have this whole system set up, what sort of things can we do with it? The simplest one is we might try and forward simulate the system. In order to do that, what we need to know is what that control force is going to be over the entire time interval we want to simulate. So if we're given this force function, as well as an initial position and velocity, then we can have this problem of finding the position over time. Make sense? Cool. Okay. And of course, respecting this equation of motion. This is pretty simple to do if you haven't tried this kind of stuff yourself. So you can do some pretty basic discretization. So suppose we want to just find, given the position and velocity at one time step, the position and velocity at the next. Well, we can discretize in time. We can actually do that in a way where we don't have to worry about velocity so much. So we write down a finite difference equation, right? This is like dx dt, but with a discrete time step. This is just a version for acceleration here that's repeatedly applying this concept. And once we do that, we get what's called a forward integration scheme. And if we mash these equations together, we get something that looks like this. And if we just rearrange this, then we get something that makes a lot of sense intuitively. Our next position is equal to our previous position. That's a good place to start from. Plus some velocity update. So that velocity update, you're just looking back one in time to get our estimate of velocity. And then an acceleration update derived from the forces acting. Pretty straightforward. Is this confusing to anyone? Awesome. Okay. So let's go back to this equation of motion. That's one thing we can do with the equations of motion. But if we think about sort of our setup with doing this animation, what we've really got here is, say, this Luxo Jr. jump. And what you tend to do in animation is you set up keyframes. So they take this idea of keyframes and they say, well, suppose you had far less frequent keyframes, right? Maybe only every 24 frames or something, which is going to be hard to interpolate between using a really dumb scheme. So suppose you just know where Luxo Jr. starts and where Luxo Jr. ends, and the velocity at each of those points. Then we might say, we'd like to find a motion which gets Luxo Jr. between those 2 points in some fixed time interval, using as little control force as necessary. And this is their principle of, and satisfying, the equations of motion. So this is their idea about how they're going to find the motion. And what this is a variational problem, specifically a 2-point boundary value problem. And this problem just says, okay, so we're given, this initial and final state, and we want to find the motion over time, where we're minimizing some cost of the force subject to the equations. So I'm going to take a digression here and talk about one of my favorite little things in basic physics, which is this beach problem. Maybe some of you know this, maybe some of you don't. So in this problem, there's a lifeguard on the shore and a person at sea who needs to be rescued. So the lifeguard needs to figure out the shortest path to the person drowning. So you might think, okay, well, straight line is usually the shortest path. And this would be true if it didn't matter how fast this lifeguard moved over land versus over sea, which probably isn't true. So if instead we suppose that the lifeguard can run faster than they can swim, which of these paths do you think the lifeguard would take? Okay, yeah. So the lifeguard would take the red one. What you may not know is that you can use the same sort of idea to derive Snell's law for the refraction of light in glass. Why is this the case? Well, light moves at different speeds through different media, right? And so we can think about a photon of light as trying to take sort of the path of least resistance. You may have heard that concept before. And this is all cute and well, but I also, let's pause a second. Hopefully this is also disturbing to some of you that we're talking about a photon as an anthropomorphized entity, which is trying to minimize some cost, right? That doesn't really jive with the whole mechanical clockwork universe hypothesis very well, right? Yeah, so as you said, principle of least action. It turns out this idea, even though it's very strange, as I just said, is the basis of modern physics. So this leads to a reformulation of Newtonian mechanics into what's usually called classical mechanics, with things like the principle of least action, the Lagrangian, where you talk about minimizing energy. And really, it's that shift in physics which makes general relativity and quantum mechanics possible. They don't really hinge on sort of the Newtonian forces view, but rather they use this principle of least action view. So it's not like a little cute thing entirely. This is the basis of modern physics. So they're dragging this into computer graphics at this point. And here's the simple problem with this particle that we're talking about with it. And this should make pretty much sense. I've been a little bit glib about this cost, so maybe we can be a little bit more explicit. And a really simple thing to do that you can get away with, unless you want to get into something super fancy, is just make this a sum of squares, right? So that's going to say, yeah, keep that small and sort of evenly distribute it over time. So if we write this all down, we have this full problem with the particle. And it turns out, if you can squint at optimization problems well, that this is just a bunch of linear constraints in a quadratic penalty, so you can just do a linear system solve and you're done with this sort of a problem. So this is a really simple one. But we can generalize this problem as well, where we talk about this. Maybe we have a bunch of particles, so we start thinking about that state as collecting a large vector of all of their positions. And those particles need to satisfy the equations of motion, but maybe we also have keyframe constraints. And maybe we want them to remain in contact, like maybe this point needs to stay on this surface during this set of frames. Or maybe these points are linked in some way, and so we want to express those linkage constraints. So we might get into a much more rich set of constraints that we want to express. And just to look at one of these, the linkage constraints, so this might be some sort of pendulum or mechanical system, like for instance the lamps, or a simple mechanical model of the human body. We can just say, here's 2 points, right? And let's take the distance between them by taking the difference squared. Normally the distance would be the square root of that, but we can also simplify this by just saying, take the length squared. Same, just as good. We got our constraint. This constraint is nonlinear, unfortunately. So we might consider these general nonlinear constraints. And I won't get into all the details of it, but basically, you can start to deal with this in your solving methods for the optimization problem by taking a linearization of that problem at some point. You do that by taking the Jacobian of these equations, which is just forming a simple matrix that represents the derivative of them. And then you plug this into something called an SQP solver, is the particular solver they use in the paper. That stands for sequential quadratic programming. What's quadratic programming? Well, I just told you that's you just solve those by solving a linear system. So they're going to solve a bunch of linear systems repeatedly, right? And take successive linearizations with that Jacobian equation. So even if you didn't get all that, here's the key thing, is this is basically what's going to happen with the code. There's going to be an outer loop where you compute the Jacobian matrix as you linearize the system, and then you solve that linear system. And a bunch of the solvers for doing that, it turns out, tend to rely on doing repeated matrix multiplication. And the matrix in question here is that Jacobian matrix. Cool? Cool? OK. The authors anticipated that all of this might be a bit much, so they included the following cartoon at the end of the paper. OK. So I talked a little bit about the math. The thing that I think everybody overlooks about this paper is the actual system they built. So there's maybe a couple key things here. One of them, I really like this sort of pithy programming quote, if you haven't seen it before. Greenspan's 10th rule says, any sufficiently complicated C or Fortran program contains an ad hoc, informally specified, bug-ridden, slow implementation of half of common Lisp. And this is relevant right now because the computer that they built this whole system on was called the Symbolics 3600. It was a Lisp machine. I don't know how many people in the audience are familiar with Lisp machines from the 80s. People had this crazy idea where they were going to build special hardware just to run Lisp. This thing had hardware-assisted garbage collection. It had 170 megabytes of disk space, when most machines at the time only had 10. And it cost $110,000 in 1983, which in today's dollars would be about $250,000. It was this thing. And it had a mouse. So I went and looked up the spec sheet for this, and amazingly, it gives this detailed explanation after being like, oh yeah, it has hardware-assisted garbage collection, and it has this strange thing called a mouse. Let me tell you, it can be clicked, pressed, to invoke choices in various contexts. Perhaps more relevant to what we're talking about here, it had an 8 megahertz CPU. There's a 32-bit CPU, and 2.3 megabytes of RAM. And it had 2 different ways of supporting displays. So it had this 32-bit color display at a relatively large resolution with dedicated frame buffers. This is actually quite high for the time, if you know anything. It also had a fairly large interactive display, which you might think, aren't all displays interactive? But we'll get to that in a second. So look at these numbers for the resolution. And the key thing here is to note that they're approximately 1,000 by 1,000-ish. This is how I like to do it, sort of on the back of my hand, or the back of an envelope. So this means you got about 1 million pixels, right? Or in camera speak, a megapixel. And this has 32-bit color, so this means you need 4 megabytes of memory to store a frame of information. And if you think about moving this around on this machine, barring any special instructions, you're going to need to do 1 million of these 32-bit move instructions, right? If you want this to animate at 30 times a second, that means you're going to need a 30 megahertz processor to copy the frame. Just to copy the frame, not to mention, trying to do something more on a per pixel basis than a move instruction. So let's look at those specs again. Right, so this thing has 2.3 megabytes of RAM and an 8 megahertz processor. If you don't realize this, in the 80s, trying to do any graphics was completely insane on these machines. The way it happened, well, how did it manage to have those frames? It had a frame buffer. The display had more memory than the CPU did. And this was that way for a while. They cost a lot of money. And clearly, we're just not going to be able to do any kind of interactive animation on this display, right? It would have to get rendered out to some form, exposed onto film or something, onto VHS, I don't know, right? And then played back via a different device. And so if you look at all this, you're like, oh, what's an interactive display? It's a display where you don't try and do this. So maybe you do a bunch of overdraw tricks, right? And you do a lot of wireframes. So you use Bresenham's line algorithm to avoid touching the entire memory. So yeah. The other thing to keep in mind is, right, you had to have people who were incredibly obsessed with squeezing every last instruction out of this thing just to be able to draw things. So they decided to run Lisp on these things. It's an interpreted garbage collected language. Great. And unfortunately, the story for those who don't know is that the Lisp machines got totally killed in the market by Moore's law and all the conventional processors, because realistically, to get things to work well at this time, you could not be sloppy with your instructions. This is the machine that they implemented spacetime constraints on. And they had a graphical user interface. So they had this idea the user could set up these boxes and connect the ports of them to form a graph where the arcs represent function composition, right? And the reason they did this is they wanted to make it easier to construct these complex systems for people who maybe weren't so good with all those derivatives in math, right? You could build this system up dynamically by composing these pre-compiled primitives. You may know about something called visual programming. This is essentially a visual programming system that they're describing. These aren't that popular in a broad sense, but for a lot of niches, they're extremely successful. So let me walk through a couple of these. In the top left is LabVIEW. Some of you may know, it lets you hook up various sensors and controllers to a laptop, especially like in a scientific lab, can be used to set up a simple signal processing system on the computer. Incredibly important to doing that kind of work, as well as for building some simple embedded systems. The one on the bottom left is MaxMSP. So that graph represents sound going through all these boxes. It's used by electronic musicians to make music, including prominently artists like Autechre. On the bottom right is Quartz Composer, which, if you remember when Mac had a graphics system called Quartz, this was provided to let people throw together programs in a simple way with it. And this particular example here is pulling an RSS feed of news and then displaying it in some cool little graphical widget. So the idea was, you could put these things together easily. Here's two more, which are particularly relevant to 3D graphics. The top one is a screenshot of Rhino, which is a 3D modeling program. And on the right is a graph set up in a subsystem called Grasshopper 3D that allows for architects and designers to create procedural forms like that shown on the left. On the bottom is a shader graph in Unity, which is a common platform for doing video games. Shading and compositing is largely put together entirely through these shader graphs. This is sort of fundamental to doing that particular niche of 3D graphics. So yeah, they thought that was a good idea, and probably it was, although people didn't really stick with it for doing simulations. Since they had this Lisp system, it makes it really natural to do things like symbolic differentiation, right? So they could save you from doing all that differentiation yourself because they just built it into the system. Because code is data, right? This code to compute something in Lisp, you can just manipulate as data. That's the way you do things. So of course you're gonna not sit there with your own piece of paper doing all your own derivatives. You might as well automate it in the system. And this is, of course, how we get that Jacobian function that we need. If you think about this graphically in terms of these boxes, it turns out things like derivatives have natural interpretations in these boxes. I don't know if they precisely did it this way, but this is another common scheme where you can think about these derivatives as sort of a parallel circuit that gets wired up to the whole thing. So this can all fit into that same language, and they can be deriving all that on the fly when the model's presented. In total, this leads to having a system. They describe it a particular way in the paper, so this is my own sort of box reconstruction of it, where you start with this graph representing the model of, say, Luxo Jr. and all of the constraints you've set up for the animation. And it can derive from that this constrained optimization problem sort of thing that I was showing you. It can also derive special code for doing the matrix computations, for taking the state and compile and sort of computing out that Jacobian matrix, as well as special ways of using that Jacobian matrix as a sparse matrix, which makes it faster to do all those multiplications. People really haven't taken advantage of this a lot since then, though the research group that I'm in, and a lot of the research I do, is very much predicated on these kinds of system designs, because we work on a lot of domain-specific languages, and we tend to use just-in-time compilation techniques. And Lisp had these ideas a long time ago, and people who are using that as a matter of course came up with a bunch of these ideas before they sort of got scrubbed out of the main narrative of everything going on. And so we have like a particular system called opt that we did recently that does this kind of stuff for optimization problems. And literally this is basically the same system diagram fundamentally. Okay, so the last thing I wanted to talk about is the impact that this work had. The two authors, again, were Andy Witkin and Michael Kass. And in particular, Andy Witkin and his students is sort of the arc of this I want to talk about. And unfortunately, Andy passed away before his time in 2010, which was very sad for the community. So this paper was presented in 1988, and shortly after that, Andy Witkin starts as a professor at CMU. And one of the early students he has is a guy by the name of Michael Gleicher, who does his PhD work on a technique called differential manipulation. The idea of differential manipulation is to do things like constraint-based drawing systems, including in 3D, by using a constraint system. This constraint system bears a lot of resemblance to the spacetime constraints. In fact, he has these sorts of diagrams in his papers showing, oh, you can do this snap-together mathematics thing to put together all this stuff. I think this whole line of work that he did is also, very underappreciated. I may be biased because I ended up building on it myself when I did a work last year with some people at Adobe, presented at SIGGRAPH, on a drawing system that we called Locality to help with icon editing. And so underneath this are a bunch of constraints in the drawing, which are being managed essentially with these same kinds of techniques. And we didn't do it in Lisp, and we didn't do it with smart metaprogramming. So I have a giant file of all these constraints that I had to sit there and derive by hand for weeks. It's not a great choice. So during this point in time, one of the papers on this work, Michael Gleicher presents at WIST 1993. WIST is the User Interfaces Systems and Technology Conference. Sits somewhere between SIGGRAPH and Kai, sort of the HCI community. They do a lot of interactive techniques, especially at this point in time. And there's two other papers in this conference the same year. The first one says, hey, it would be really good if we did animation support in our user toolkits. Slow in, slow out test. And a really good idea here is to use all these principles of animation from somewhere earlier. The second paper is even more explicit about this idea, animation from cartoons to the user interface, and has a whole list of techniques, that many of which are pulled directly from the Lassiter paper. And here you can see the motion of a window where it says, oh, it'd be really good if you have it sort of like pull back a bit and then move, if the system is moving this window of its own volition, so that the user's eye is drawn to that window and sees what's occurring. This is a pretty good idea. A year later, in 1994, at SIGGRAPH, a system called Teabag gets presented. This is done by a bunch of people working at Sun. And I'm not sure, maybe this is different than Sun Systems. In particular here, you can see this sort of 3D spring system, which is very similar to the stuff in Michael Gleicher's work, as well as these constraint graphs, some of which are undirected and others of which they have this idea coming in of having these directed constraint graphs, which is very helpful if you're thinking more data flow. And the first author on this paper from '94 is a fellow by the name of Connell Elliott, who goes on in 1997 to write a paper. What did I get wrong? Oh, yes, Connell Elliott. There we go. There's Connell. And he goes on in 1997 at the International Conference on Functional Programming to present a system called FRAN, which introduces this concept of functional reactive programming. And the reason for having FRAN is so that you can do animation. And as some of you may know, this concept has now leaked entirely into the JavaScript front-end stack with systems like React, or maybe if you want to be more esoteric, the language Elm, which are all based on reactive programming. So that's another sort of random path from there. Another student that Andy Witkin has at CMU is a fellow by the name of Zoran Popovic, who does a lot of his work on animating human characters and really sort of takes off with a lot of the motion capture data becoming available in the late 90s. One of his key works he does here is on physically based motion editing. So here they take the idea of the space-time constraints, but apply it to editing some motion data that happens to already exist, perhaps by capturing it. The idea is you do all these edits subject to physical constraints. And this is really the start. This is like sort of on the ramp up of a lot of work on physically based animation of human-like characters, which has gotten only more sophisticated as we get towards the present. I'm not going to go into it all in detail, but yeah, basically trying to walk cycles of people entirely from scratch at some point, right? Just based on these physical principles, which is a particularly challenging thing to do if you know anything about sort of bipedal walking, just staying balanced and not falling over and face planting is very difficult. He also has some students. I was actually up at UW and worked with him. And met some of these students who started looking at animal motion, such as birds or various creatures. In particular, this bottom work by Kevin Wampler, one of his students, looks at this question of, hey, can we predict what the gait of a character is based on its morphology, right? Like, what are its limbs? What sort of muscles does it have? Where's that mass? And he publishes a paper. He published a paper somewhat recently looking at this. Kevin really likes dinosaurs, so he wanted to see if you could take a dinosaur skeleton and figure out how the dinosaur should walk from it. And you can see this is really these echoes of these questions that Witkin and Kass posed back in 1988. Then in 1998, Andy Witkin rejoins Michael Kass at Pixar with the research team there. And that's sort of a limited slice through some of the history there, or future history from the paper. So that's most all I have to talk to you about. As I said, I was going to discuss these 4 things. I hope I did it satisfactorily. And I'd like to take any questions you all have.
Who has a question?
So does this predate neural networks, or is it after the neural networks start getting developed?
What do you mean by neural networks?
By neural networks, I mean the backpropagation algorithm specifically.
Backpropagation probably predates this.
Because it's very similar. So you're taking
it's derivatives. Backpropagation is just gradient descent.
Well, it's derivatives on an operation graph, and then using numerical optimization to find parameters that you weren't explicitly given for that operation graph.
Yeah. So that's a good point. Something I didn't mention in the system design is that things like TensorFlow, and this has taken a while with the sort of deep network stuff, because everyone's reticent to do the domain-specific language thing, but it's a domain-specific language. It's, can be JIT compiled. It benefits from that same kind of system design, 100%. People should have realized that earlier, I think, but you really can't do a neural network library very well and have it be very performant without using these sorts of techniques.
But I think, if you replace the quadratic whatever optimization algorithm they used with stochastic gradient descent, I think it might literally be a deep neural network.
Yes, in the sense that you can encompass everything under that. The data is usually not organized in layers in the same sort of way.
Okay.
It's like, these will tend to be more heterogeneous, so you're going to have a smaller state vector. You're not going to have like a bunch of layers that you necessarily want to propagate things through to the same degree. And then you're going to have all kinds of different constraints sticking onto different variables because you're dealing with like a person,
okay,
right?
so
Which doesn't have the same topology or...
Right, so it's not that you have one loss function at the end that all your constraints are incorporated in the one loss function. You can have extra constraints that are added at different parts of the network, right?
Yeah, okay. Exactly. Also, if you do it over time, then actually that time sequence is going to become a very strong structural element. So if you look at the matrices that come out of this, they're going to fit into a category called sparse banded matrices, which generally I wouldn't think of the deep net stuff as that.
So if frame buffer rates were the problem with the symbolics machine, what is today's problem in performance?
That's an interesting question. I think I wouldn't say that is the problem with the symbolics machine's performance. It's just a way of drawing out how resource limited everything was in the mid-'80s. That's true for a wide range of applications. It's just very easy to make that clear for graphics. And it's something that people forget. Like even today, if you want to process an image on a gigahertz processor, if you just do that without any parallelism, right, and you have 1 million pixels, you only get 1,000 instructions per pixel. That's crazily less than most people are used to thinking about, unless they're doing like low-level networking hardware, I think. But of course, there's parallelism available. So I think really the performance challenge for a lot of things today, what I'd at least, what a lot of my research is predicated on is that people need to take advantage of parallelism, both in GPUs, SIMD parallelism, multi-core, especially when you're doing these sorts of numeric computations, simulations and the like. And exploiting all of that is extremely difficult. Sorry, I'm giving you half my research pitch. So if you have a DSL, it turns out you can do a bunch of that stuff automatically for a particular problem class. I think that's a good idea, but I'm biased.
So I liked the talk about positioning, where the sort of tricks and special cases about making animation look good could be reduced to physics. And I wonder if you've seen in the UI field, could user experience be reduced to cognitive science, right? All these special cases about different kinds of controls. Is it really all unified?
So my personal feeling when I talked about all the positioning stuff is I'm trying to describe what I believe happened and the way that I believe technical communities are. I actually personally, philosophically disagree with that fairly strongly. But that's an interesting question. Some of the things I didn't talk about in the talk because it seemed like it was too much of a random tangent in my brain. But yeah, so suppose you take the Lassiter paper, right? And you say, we're going to automate it. But maybe the way we're going to automate it isn't by reducing it to physics, right? We could try and reduce it to cognitive science. If you're interested in that, you should definitely read the thesis work of Anka Dugan, I want to say her last name is. She's now a professor at Berkeley. She was at CMU for her thesis. And she did a lot of stuff on this this idea based on cognitive science modeling of saying, suppose I'm an agent thinking about another agent thinking about me. And suppose I want to apply this to a robot that's trying to, like cook with me and grab things on the table. Then one rationale for how that robot might move is not the most efficient path in terms of the physics, because I'm there as well, and the robot needs to communicate its intention to me. So if I have I don't know, this microphone here and this, and there's somehow both glasses on a table or whatever, and I just reach forward like this, am I going for the microphone? Or if I'm going for the glass, I'm going to do this. It's a less efficient motion path, but people understand that better. And you can absolutely apply that same idea to a bunch of these animations, right? Like anticipation doesn't just have to be about, I need to create momentum to jump. It can be about, I want to make sure the person's looking here. It's a very different explanation for the same principle.
So I was wondering, the formulation with the quadratic cost is basically optimal control theory. I was wondering if they are aware of that or they rediscovered it.
Yeah, they refer to optimal control theory.
So
the community doesn't like really catch on quite as fast.
Okay.
So there are a couple of people at this point who really knew a bunch of physics and math involved, and then there's a lag in getting everybody else who's practicing up to speed on that stuff, which is sort of an interesting lesson, I think, for research communities. Some of that optimal control theory stuff also comes in very strongly. Sometimes it gets called reinforcement learning or dynamic programming. So everyone seemed to rediscover this in the early 2000s. There was sort of 3 concurrent papers, one of which titled Motion Graphs, which all gave approximately the same solution to how can we use all this motion capture data. And they all end up doing dynamic programming, and it all boils down to, in some sense, precisely that, optimal control theory.
Any more questions? All right. Thank you so much.